Assalamualaikum and greetings. I am Syahiera Erissa Binti Shahriza with matriculation number of S5643, a final year student in Bachelor of Science in Chemical Sciences. I will be presenting my final year project which is the computational analysis towards ortho, meta or para-pseudo-finite Thiosemicarbazone isomers via Gaussian zero-net software. My research project will be supervised by Dr. Uwaisulqarni bin Osman. Here is the table of contents which I will be discussing on introduction, methodology, results and conclusion. First, let's begin with introduction. Thiosemicarbazone, or can be known as TSC, is an organosulfur compound where it consists of sulfur atom that was placed between both of nitrogen atoms. TSC can be produced by reacting semicarbazide with any selected carbonyl group such as aldehyde or ketone through a condensation reaction. It is well known among researchers due to its metal cleaning properties in order to allow them to create metal complexes compound with the special geometries. It has also been reported that this metal thiosemicarbazone had discovered in few applications in biology. Next, we move on to the problem statement. Due to the ability of thiosemicarbazone to act as a ligand for transition metals, there have been extensive research. Most previous researchers have concentrated on pharmacological features due to their efficacy in terms of biological activity. However, only a few of them have studied and discovered the effects of ortho, meta or para-thiosemicarbazone isomers that could be useful in a wide range of treatments. To overcome this problem, advanced studies, especially the structural characterization of the molecule, need to be employed. This research consists of three main objectives, which are to study the theoretical analysis of HOMO-LUMO, MEP, FTIR, NMR, and UV-VIS of the molecule, besides to analyze the effects of electron withdrawing groups on absorption on both IR frequency and UV-VIS energy, NMR shifted HOMO-LUMO energy and MEP region. And lastly, to perform the quantum mechanical calculations via DFT by employing the standard 6311G basis set with the Gaussian zero-9 software. Next, for the methodology part. In this study, the methodology is based on computational work utilizing with Gaussian 09 and Gauss-View 5.0.9 software package program. The quantum chemical calculations completed have been carried out at battery LP level with the regular 6311G selected as basis set due to the standard theory level for carbon, hydrogen, nitrogen, sulfur, and fluorine elements in Gaussian zero-9 software. These are the steps involved in this research. Next is the results obtained from this research. In optimization data analysis of these isomers, based on the results, A1 has 7cc, 4ch, 4cn, 4nh, and 1nn and 101s bond length. Meanwhile, for A2 and A3 molecules, they also have a similar amount of the bond present in A1 molecule. The bond length was extended in order to retain the repulsive force between the ring and chain charge clouds in these isomers. Moreover, the bond length for Cn in A1, A2, and A3 isomers were observed at 1.1568, 1.1552, and 1.1558 respectively. According to a prior study, the differences in this value could be due to the effects of pi conjugation between the phenyl ring and thiosemicarbazone fragments. Moreover, the CC bond length in the 6 member ring of A1, A2, and A3 was observed to fall within the range of 1.39 to 1.4. Previous researchers state that the value for the bond length of CH might be slightly different due to the charge distribution of the carbon atom of the phenyl ring. The electron withdrawing group attached to the phenyl ring in A1, A2, and A3 may reduce the density of electrons in carbon atoms bonded to the ring. Hence, the carbon atom on the phenyl ring will distort the valence electron cloud of hydrogen bonded to them, result in higher carbon force constant and lower the bond length of carbon. Next, for the results obtained in bond angle. The increased value in bond angles above 120 might be resulting from hyperconjugative interactions during bond formation. The bond angle of C3 and C15 for A1, A2, and A3 isomers was observed at above 132. The results obtained in this analysis show that the energy gap of the thiosemicarbazone isomers A1, A2, and A3 molecule is 4.4101, 4.5495, and 4.5149 respectively. This indicates that the A2 molecule has higher energy gap compared to the A1 and A3 molecule. This is the list of formula and chemical parameters of thiosemicarbazone isomers. To be summarized, it shows that the smaller energy gap will contribute to higher reactivity and greater intermolecular actions, which may approach degeneracy. When molecules approach degeneracy, the molecules become more stable, which can easily donate an electron from HOMO to a LUMO region. The molecule will become more stable and lead to a soft system. Based on the table above, the value for energy gap in increasing order are as follows. Therefore, it can be concluded that A1 has the most stable molecule and tend to be a soft molecule compared to A1 and A3 molecules due to the smaller energy gap. For MEP analysis, based from the obtained results, the negative regions are mainly localized on the sulfur atom of the thiosemicarbazone group, indicates that there is a possible site for electrophilic reactivity. In contrast, the positive regions are localized on the hydrogen atom, showing the site for nucleophilic attack. According to the result, the center moment N shows the red region due to the contribution of lone pair electrons of nitrogen atom. Additionally, the 01S in thiosemicarbazone group shows a yellow color on the electrophilic region. The hydrogen bond bounded with the nitrogen is mainly localized on the blue region and suitable for nucleophilic attack. Initial zone, which is the green color, indicates the hydrogen bonded to the phenyl ring. In FTIR analysis, the theoretical FTIR spectra of the thiosemicarbazone isomers were recorded in the 3500 to 600 region. The infrared analysis showed the presence of 7 main absorptions, namely NH, CH, CC, C-N, CN, and N, and C-S reaction vibrations. We assign all the possible absorption in IR spectrum. We observe that the stretching absorption for NH group is commonly in the range of 3500 to 3200. Both N and H stretching vibrations remain symmetric due to the dominating nature of the group. In CH stretching vibrations of aromatic, the vibrational modes were generally observed in the range of 3100 to 3250. This region is hardly affected by other substituents in which the nature and position of the substituent seems to have only a small effects on the modes. Next, in C01N vibrations, the characteristic region of the functional group is within the range of 2200 to 2350. The stretching vibrations of the CC are commonly appeared between 1200 to 1650. In these medium CC vibrations, the type of substituent group has only little effect on the vibration. Next, in CN absorption, according to all reports, it occurs between 1380 to 1160. The CN stretching vibrations are moderate to intensely active. Then N stretching has also been reported in the literature at 1100 to 930. Lastly, for C01S, the present study assigns the band at 786, 744, and 729 in the FTIR to the C01S stretching vibrations for A1, A2, and A3 isomers. Here is the FTIR overview for A1, A2, and A3 isomers. In this research, the electronic spectrum of the isomers in A1, A2, and A3 molecule exhibits only one band in the region, in which resulting in the absorption maximum of 268, 276, and 260 respectively. All of these Thiosemicarbazone isomers were assigned to the pi to pi star transition. Based on the results obtained, the strong transition was observed at 82 peak of 276 with maximum oscillator strength of 0.7189 with energy gap of 4.5495. The appearance of shoulder at A1 and A3 isomers were common for highly conjugated system and is often solvent dependent. This result shows that A2 has the highest value of oscillator strength compared to A1 and A3 isomers. The higher conjugation will lead to the lower energy difference in the HOMO and LUMO region, where the absorption peak is redshifted to a longer wavelength. In the Proto NMR, it shows that the most of the chemical shift in the aromatic ring for the all studied molecules in the range of 6 to 10 ppm, since there is no further influence of hydrogen atoms. Besides, the hydrogens can modify the chemical properties of the targeted compound. The appearance of singlet signals by aliphatic protons, CH and CH3, have appeared in the range between 5.9 to 6.5. Additionally, the appearance of singlet peaks at thioamide and H group is in the range between 3 to 9.95 ppm. Lastly, in carbon NMR, the chemical shift of carbon in aromatic ring usually shift above 100 ppm, which was quite normal. The range of carbon NMR chemical shift in these isomers were in the range between 120 to 138 ppm. Moreover, the thioamide C01S carbon can be observed at carbon 15 with the chemical shift of 180 ppm. Due to the intramolecular hydrogen bonding of the compound and the electronegativity of sulfur atom, it may alter the resonance for C01S, which can be slightly deshielded to higher chemical shift. In conclusion, the influence of the different position of the cyanide group C01N at ortho, meta, and para position has shown the physical and chemical properties of all the targeted compounds. The findings reveal that all the compounds in these findings are chemically reactive. It found that 3-cyanophenylthiosemicarbazone, which denotes as A1, has greater reactivity than others. The UV-VIS supports this finding that shows an intense absorptions at 268, which is pi to pi star transition. In terms of the 4-cyanophenylthiosemicarbazone A3, the chemical potential of the compound has higher value indicates that the molecule have outstanding stability but are the least reactive. Consequently, 3-cyanophenylthiosemicarbazone A2 has the lowest chemical potential, which is more reactive but the least stable. Moreover, for the proton and carbon NMR, the influence of the different positions may decrease the electron density away from the nucleus, which will deshielding the nucleus. This has resolved a few crucial parameters of Thiosemicarbazone isomers A1, A2, and A3 to help researchers develop potential products that might be useful in drug designing or other valuable applications related to these isomers. For the recommendations for future works, these findings has been recognized as potentially beneficial as a reference for experimental Thiosemicarbazone isomers compared to the theoretical data. So that's all for my final project. I hope you can learn something. Enclose is my references and turn in result. That's all from me. Thank you for your attention.